All right, ladies and gentlemen, today we're going to be talking a little bit about chemical equations. Now, we've already been talking about chemical reactions and how a chemical reaction is different from a physical reaction. A physical reaction or a physical change is when something is changing its shape or its form, but it stays the same molecule. A chemical reaction or a chemical change is when something new is being produced. A chemical reaction is kind of what we see or what we know is happening chemically. A chemical equation is a way to write that down. It almost looks a little bit more like a math equation. That's why we call it a chemical equation. But we use symbols for our elements and our chemicals. And instead of an equal sign, we use an arrow to show the progress of the reaction. When a chemical reaction occurs, there has to be some sort of new substance formed. This is a pretty amazing video of a red gummy bear with some potassium chlorate, and I'll provide a link for you to watch this a little bit later. So we have three major types of chemical reactions. We have synthesis, decomposition, and replacement. Over here on the right-hand side, I have given you some equations with A, B, and C. Those letters could represent any of the elements from the periodic table. So with synthesis, we have atoms that are combining to make more complicated compounds. This is an example of pure sodium, which is a soft metal, being combined with chlorine, which is a green poisonous gas. And when they go through this reaction, they make sodium chloride, known to you and me as regular good old table salt. Here we have the decomposition of water. Decomposition is when a larger molecule is separated. Those bonds are broken into its smaller individual pieces. Here we have water being zapped with a little bit of electricity into hydrogen and oxygen. And here we have an example of a replacement reaction where propane, like your barbecue propane tank, is combining with oxygen, and that produces water and carbon dioxide. Now what I'd like you to notice is that the propane has carbon and hydrogen bonded together and oxygen all on its own. And after it's gone through the reaction, we now see that carbon is bonded to oxygen and hydrogen is bonded to oxygen. So let's go back and take a look at that decomposition reaction. Here we have good old water, H2O, being zapped with a little bit of electricity to form hydrogen gas and oxygen gas. But what I'd like to point out is if we take a minute and we kind of draw a line, over here on the left-hand side, we have our reactants. Over here on the right-hand side, we have our products. And I want us just to take a minute to count how many of each type of element are on each side of the equation. So on the left-hand side, I can see that I have 2 hydrogens and 1 oxygen. On the right-hand side of the equation, I have 2 hydrogens and 2 oxygens. So what happened to that extra oxygen? How did we get an extra oxygen? So the quick answer is that we can't just have atoms come and go as they please. There's this whole thing called the law of conservation of mass that says that matter cannot be created or destroyed. So this is where this whole idea of balancing chemical equations comes in, this whole idea of stoichiometry. So what we can do is we can add a number in front of any of these molecules, a coefficient, and that will help kind of give us a ratio of how these ingredients work. So if I have 2 oxygens over here on the left, if I have 2 oxygens over here on the right, and I want to get 2 oxygens on the left, what I need to do is I need to put a 2 in front of that H2O. Now that 2 will distribute to both the hydrogen and the oxygen, and when you put that 2 in front, it essentially multiplies by each of those atoms. So now I have 2 times 2, now I have 4 hydrogens on the left, and 2 times 1, now I have 2 oxygens on the right. So this has helped balance out my oxygens, but now I need to take a look and balance out my hydrogens. So on the right-hand side of the equation, in front of that H2, I'm going to put a 2 in front of my H2. So now I'll have 4 hydrogens on the right and 2 oxygens. So this is now more of a balanced equation. I can take a look at how many of each type of atom do I have on the left-hand side versus the right-hand side. I have 4 hydrogens on the left and the right. I have 2 oxygens on the left and the right. If I wanted to, I could put a little 1 in front of that oxygen, but that's now is kind of the ratio of how these molecules interact during this reaction. For every 2 water molecules that go into this decomposition reaction, it will produce 2 molecules of hydrogen gas and only 1 molecule of oxygen gas.